Hi everyone, thank you for joining us today. Good morning or good afternoon, depending on where you are in the world. My name is Bill Ricksecker. I'm a product manager here at Allied Machine Engineering. Today we're going to be going over the XT Pro. It's one of our high penetration replaceable tip drills. We're going to be going over a little bit of a presentation, just kind of going over the basics, go through the insert, the holder, and then we're going to go through some case studies at the end. And then after that, I'm going to go over and switch it over to Rob Brown, and he's going to go over to some of our presentations so you can see the drill going in action. So I'm going to go ahead and switch over, and we're going to go ahead and get going. So first of all, just kind of an outlook on the inserts themselves. We offer from 11 to 35 millimeters. We have a specific coating, a substrate geometry, and that's all per material call out. So we have them separated into ISO material specifications. Kind of make it easier on you when you're picking your insert for your holder. It's going to be a little bit easier because depending on if it's a steel, it'll go into our P, a cast iron in our K, and then like aluminum's going in the N geometry. So we kind of did the work to kind of say, hey, depending on whatever material you have, here's one insert that'll get the job for you. So I'm going to go ahead and move forward. So the first one we're going to go over is the P geometry. So this one's designed to provide increased penetration rates and tool life and steel applications. So what we wanted to make sure was that in the broad scope of steel, we needed to make sure we can get the chip formation and the little bit tougher chip formation materials, but then we also wanted to provide the strength going into some of the harder steels to kind of be able to withstand what that would put the insert through. So Allied's multi-layer AM420 coating, so that's going to help. It increases heat resistance and improves tool life in those steels. So next is going to be our K geometry. So that's going to be for cast irons. So this one's, again, uniquely designed for cast nodular iron applications. Geometry includes a corner radius for improved hole finish and heat dispersion. The Allied's multi-layer AM440 coating provides increased abrasion resistance and tool life. So typically with the K geometry and going in cast irons, really chip formation is not something that you usually struggle with. So with this insert, we kind of decided to make it as tough as possible to be able to get the tool life that you're hoping for and expecting going into the cast irons. So next is going to be our N geometry for non-ferrous materials. So this one's designed for applications in aluminum, brass, and copper. The geometry yields excellent chip control in these softer materials, and this is actually going to have our tin coating. Gives the versatility to run in a variety of materials while reducing buildup. Typically when you're going into the aluminums, that's where you're going to see that buildup edge. So we found with that coating, that reduced the amount of the buildup edge that you could see. So next I'm going to go ahead and go over the holders. So with the XT Pro, we did redesign the holders a bit from our standard XT holders before. So what I'm going to do is I'm going to go and switch over to this screen over here and kind of show you what we've done. So the first thing is the new flute design. So again, we increased the capacity up to 12%. So you can kind of notice here with these flutes, they're a little bit wider than normal. That's going to help get the chips out of the hole much faster and reduce the possibility of them building up at the bottom of the hole and causing immediate failures. We also added additional coolant outlets in the flute directed toward the cutting edge. So what that's going to do is that's going to reduce the heat produced at entry and effectively improve the tool life. So you can kind of see here, I'm going to point to it as best as possible. So here's that additional coolant outlet. What we were finding is when you're going in that high penetration and that increased feed rate, the tips of the inserts themselves were actually burning up when they were going in because it didn't have that coolant hitting the point of the insert upon entry. So what you'll see in these demos as we move forward, you'll see a stream coming out of this coolant outlet and then also a stream coming out of this coolant outlet to help with the ODs of the inserts, but also help protect that point of the insert. The other thing we did was added dual gun drill for increased coolant flow. So we wanted to be able to feed both of those, the additional coolant outlets plus the original coolant outlets that we had before. So we found that by adding these dual coolant gun drills, it was able to provide the volume that we were looking for. So these these holders are available in the straight flute configuration that you can see here. And these are available in 3 times D, 5 times D, 7 times D, and 10 times D. Okay, go ahead and switch back. Okay, so now what I'm going to go ahead and do, we went through the basics, all the inserts, kind of what we have as far as the PK and N. Went through the holder design, kind of showing what the improved holder design will do for you. Now I'm going to go ahead and go through a couple of our case studies that we've thrown in here. So our first case study was going into a AR upper receiver. In this case, the competitor was running a solid carbide drill, and the customer wasn't really looking to increase the parameters. They were looking for more of an increase in tool life. So we kept the running parameters the same from the solid carbide to the indexable, but we were able to increase our tool life from 2,700 inches all the way up to 9,000 inches by switching over to the XTN insert. So the next case study, so this one was actually going in an ATV suspension part. And in this one's a little bit different than the last. They were looking for that increased penetration rate. So the other competitor high penetration drill was running the cycle time of about 23 seconds or 8 inches per minute. And the XT Pro K came in and was running 43.7 inches per minute and took their cycle time all the way down to 4 seconds. So the tool life stayed the same from one to the other, but we were able to increase the penetration rate, therefore lowering their cost per hole. Okay, so that is actually all I have for the presentation part of it. What I'm going to go ahead and do now is introduce and bring in Rob Brown. If you've been in our Allied live shows before, I'm sure you recognize him, and he's going to go ahead and take us through the demos today. Thanks, Rob.
Thanks, Bill. Hi, for those of you who don't know me, my name's Rob Brown. I'm the engineering trainer here at Allied Machine and Engineering, and we're going to run through some demos for the XT Pro product today to show you the capabilities of this in several different materials. A little bit of background on the machine. The machine we're going to be running today is a Haas VF3 vertical machining center that's 30 horsepower. For most of these demos, we're going to have the coolant set at 400 PSI, with the exception of the last demo where we do deep hole drilling, we're going to have it actually set at 1,000 PSI. But what we're going to be running is the P geometry, the K geometry, and the N geometry to show you how those work in the materials as Bill said that they were designed to be used for. So we're going to start off with the first demo. We're going to be running a 3 times D GEN3SYS XT Pro holder with a 20 millimeter diameter P geometry insert running in 4150 alloy steel 28 to 32 Rockwell. Speed and feed we're going to be running is 310 surface feet a minute and 15 thou per rev, which in metric is 94.5 meters a minute and about 0.38 millimeters per revolution. So let me get my safety glasses on here. Dave, we're ready. We're going to go ahead and run this. We're going to run a single hole. Once again, 400 PSI running 310 surface feet per minute, 15 thou per rev, which is 94.5 meters per minute and 0.38 millimeters per revolution. Okay, so there we go. And with the 4150, it's a nice material to kind of benchmark with and show you the chip formation capabilities. So we're going to gather up some chips here and take a look at them. And we'll show you those underneath the screen. Did you happen to notice what the load was, Dave?
Yeah, it was about 85%.
Okay, so the load was about 85% on the tool. So take a look at the chips that we get. And remember that the geometry on the XT Pro has both axial and radial rake to it. So it's going to make more of a traditional, like a twist drill type chip form that's going to be more of a cone shape, and that's what we see here. So the chip formation is nice and good. And we're going to have Dave take the part out so we can take a look at what the hole finish looks like and that kind of thing. Once he gets things blown off back there, we'll take a look at that and see what it looks like. So, hang on just a second, he's working on it. We got to get him to blow it off here so you can take a look at it. And here we go. So once again, the diameter of this hole is 20 millimeters in diameter using a 3 times D holder. So here's the finish that we get. Okay, by feel there, it's probably somewhere around 100 RA, somewhere in that neighborhood, but it's a nice clean cut. The exit burr on the back side, relatively smooth. there really isn't a burr on either end of it, so it came out pretty good. And the quality of the hole looks pretty nice. So that's P geometry, running in alloy steel, 4150 material, 28 to 32 Rockwell. So for demo number 2, we're going to show you what the K geometry does, and that, remember, is designed for cast irons, both nodular and gray irons. We're going to use the same holder. It's a 3xD XT Pro holder using a K geometry insert that's also 20 millimeters in diameter. Speed and feed we're going to be running is 465 surface feet, feed rate of 18 thou per rev, which in metric comes out to 141.7 meters per minute at a feed rate of 0.46 millimeters per revolution. So we still have the coolant pressure set at 400 psi going through the tool. And you know, if you remember, with nodular cast iron, the chip formation is going to be fine. Normally when you're looking at cast iron applications, it's more about how long does the tool live and how fast can I cut the hole. Because since cast iron is a discontinuous chip forming material, it's going to make a decent chip every time that you do it. So Dave, if you're ready, let's go ahead and run this. Okay, so once again, 20 millimeter diameter nodular cast iron, about 200 Bernal in hardness, and we're running 465 surface feet, 18 thou, which is almost 142 meters per minute, about 0.46 millimeters per rev. So we'll grab some chips here and show you those. But you know, as I said earlier, the chip form for cast iron is going to be it's going to be good chip formation, but we'll take a look at the quality of the hole here in just a minute as well. So I'll get a couple samples here to show you. Thank you, sir. Okay. So as we remember, cast iron is a discontinuous chip forming material. So as we take a look, you can see it just breaks into small pieces, and even whenever it does start to actually form, you know, you can just kind of crush it up and it breaks into smaller pieces because, well, it's cast iron and that's what it does. So as Dave gets the part out of the machine, we'll take a look at what the hole quality is and any kind of exit burr, because that's sometimes an issue that you get into with cast iron, is not that you actually push a burr as much as it kind of creates frittering around the bottom of the hole. So let's take a look at what we get here. So you can see the hole quality is actually quite good. Honestly, it probably came out a little bit better than what we got with the 4150. Exit burr, it's got a real small exit burr on it. I mean, you can feel it, but you can't even see it. So it's nice and small. And that's what you hope for whenever you're talking about cast iron. And the geometry on the K geometry insert is designed to help minimize exit burrs. It has a corner radius on it instead of a corner clip. It's going to help minimize that frittering that happens at breakout. So for demo number 3, we're going to have a little bit of fun with this. We're going to run 6061 aluminum that's 80 to 100 Bernal in hardness. We're still using a 3xD XT Pro holder, 20 millimeter N geometry insert running in aluminum. And the speed and feed we're going to run this one at is 1,547 surface feet per minute and about 27 thou per rev. That equates out to 200 inches a minute in penetration rate. In metric, that's 471 meters per minute and 0.68 millimeters per revolution. So we're going to do a 4-hole pattern for this because of the fact that we are drilling so quickly. I mean, 200 inches a minute going through an 1.5 inch material is not going to take very long. It'll also give us the opportunity to grab up some chips. I do believe we changed the coolant pressure to 1,000 psi on this application as well. Because of the amount of chips that we're creating in such a short amount of time, we want to make sure we have the coolant set to make sure we blow that coolant out, or that chip out, as quick as we can. So we'll get that upgraded from 400 psi to 1,000 psi to go along with it. And we're going to drill 4 holes with this one because it's going to go pretty quickly as we go through that. So Dave's getting the thing all adjusted here, so we go to 1,000. Looks like we're there. Dave, are you ready? Just about, he says. So that means I got to talk more to fill the air with my pleasant voice. So once again, speed and feed we're going to run is 1,547 surface feet per minute, 27 thou per rev, 471 meters, 0.68 millimeters per revolution, 20 millimeter diameter, and 6061 aluminum. So here we go. All right, so it's running about 165%. The thing is, whenever it runs like that, it's in the cut for such a short amount of time, it's actually kind of hard to measure what the load is on the machine, because, you know, obviously whenever you first touch down with a tool, it always kind of spikes up a little bit. But we're going to go and grab up some chips and show those to you. And remember, we ran about 27 thou per rev. I think it's 0.68 millimeters per rev, I think. Yeah, 0.68 millimeters per rev. So these are some pretty big chips that we're getting out of here. So you can see, like, the chip form's really nice. And you can see the thickness of the chip because of that feed rate that we're running is pretty heavy. But the chip form actually was really good. And when it was running, we didn't hear any strange noises or anything like that. So the tool, while it was running, you know, incredibly fast with that 1,000 psi of coolant going through the tool, we were able to evacuate the chip pretty well. So here's the holes that we made. So you can see the finish on it is a drilled hole finish. Quite honestly, if we wanted to make a better finish out of it, we could just adjust our speeds and feeds, but we wanted to show you the capabilities from a penetration rate standpoint, so that's why we ran it at 200 inches a minute. The exit burr, even though we were running at really high feed rate, the exit burr is actually quite small, so it did a really nice job going through that hole. So it gives us the ability to run really high penetration rates in materials like 6061 aluminum. All right, so now we're going to get ready and do our last demo for you. And the last demo that we're going to run is we're going to go back to that 4150 material, but now we're going to do a deep hole drilling exercise. So we're actually going to be drilling using a 10 times D tool. We're still a 20 millimeter diameter, but we're going to drill the pilot hole with that 3 times D tool and establish the hole. And we're going to come in with a 10 times D hole tool, and we're going to drill it about 7 inches deep, 7.5 inches deep, I think it is, somewhere in that neighborhood. But in the book, when you're looking at the speed and feed that you need to run, if you remember when we ran that short tool just a couple minutes ago, we ran it at 310 surface feet and 15 thou per rev. If you look in the book, for those longer tool lengths, we do actually put in a reduction. So we're going to take those numbers and multiply them by 0.7, so we're going to reduce them by 30%, which is going to have us at a speed and feed of 217 surface feet a minute and 11 thou per rev, which is that 310 and 15 multiplied by 0.7. In metric, that turns into 66.4 meters per minute, 0.28 millimeters per revolution. But we're going to follow the Allied deep hole drilling guidelines for this. What we're going to do first is come in with that 3 times D tool, drill it a couple of diameters deep to establish the hole. And if you remember, that does 2 things for us. It creates a really good starting condition for us because we have very little taper, bell mouthing. Position's going to be as good as it can be because we have a short rigid tool to create that initial cut. And the other thing that does is actually turns your workpiece into a bushing for that longer tool. So whenever we come in with that longer tool, it encapsulates the margins of the drill and prevents whip because that's why we practice the deep hole drilling guidelines. So we're going to drill it with that short tool, establish the hole. The next thing we're going to do is come in with that longer drill. Whenever we go to lower it in, we're going to run it about 50 RPM as it goes down in there to minimize any kind of whip. Once the margins get engaged, it's going to be about 1/8 inch from the bottom of that pre-existing hole. You'll see the coolant kick on, the tool will come up to speed, then we're going to drill the hole at that 217 surface feet, 11 thou per rev that we talked about a minute ago. Whenever we get done with the cut, it's going to go back to that 50 RPM, so the tool doesn't go into whip whenever it comes out. We've done the deep hole drilling guidelines in a couple of different applications, both with XT Pro, TA Pro, TA. Any tool that Allied has that we sell that's 9 times D or longer, we recommend that you follow these deep hole drilling guidelines to maximize the safety of your application. So, Dave, if you're ready, we're going to do the pilot hole first. So we're going to come in with that 3 times D tool. This is a 20 millimeter diameter P geometry insert running 217 surface feet, 11 thou per rev. We still have the coolant set at 1,000 psi because when we come in to do the deep hole drilling application, we want to make sure we keep those chips moving. So we'll take a look at the chips real quick whenever we do the pilot hole to make sure that we're okay with the chip form at that 217 and 11. Okay. And the load is about 60%. Okay. So we'll grab up a chip here and just take a look at it. I'm not going to gather them up like we did before. We're just going to go and just take a quick look at them, make sure that we're okay with the chip form. Because once again, if I'm not okay with the chip form whenever I'm doing a shallow hole, I'm certainly not going to be very happy with the chip form when I go to do the deep hole. So let's take a look at what we got here. It's very similar to what we got with the 350 and 15, or 310 and 15 that we ran a couple of minutes ago. So we're still getting those nice cone shapes and everything. So this is the kind of chip form that we want to have to be able to evacuate the chip whenever we come in to do the deep hole drill. Okay, so set that down. Dave's going to get ready for the longer tool. So that way we can get that longer tool in there to run in. And remember, whenever we do it, we're going to come in slow at that 50 RPM. We're going to lower it down into about an 1/8 inch from the bottom of the hole. And then we're going to kick on the coolant, spool it up to the RPM and feed rate that it needs to be, and we're going to drill the hole. Now, while it's drilling, what we want to do is we want to make sure the load meter's steady. We want to listen to the sound of the drill because the pitch should be a fairly consistent pitch as it runs. We shouldn't hear any low pitch grumbles or anything like that. And then if you watch the video as the tool's running, what you want to see is the chips basically spraying out of the hole with no restrictions, because if they're just barely making their way out of the hole, it's a good indication that maybe we don't have enough coolant pressure to do the job. And if we don't have enough coolant to adequately evacuate the chips, our options are to either come up with a coolant system that will allow us to do that, or we'd have to reduce our speeds and feeds because the amount of coolant that you need is directly in relation to the amount of chips that you produce. So the cubic inch removal rate would have to be reduced, and how you're going to reduce that is minimize your speeds and feeds to make that happen. So Dave, are we ready? Let's go ahead and run the deep hole drilling. Okay, so what you're going to see is the tool's running at 50 RPM. It gets down inside the hole. Then once the margins are trapped in the hole, you're going to see the coolant come on, and it's going to spool up an RPM, and it's going to start to drill. Okay? So whatever the tool, so there you go. So what we should hear is a fairly consistent sound as it cuts, and it's running about 55% on spindle load as it's going through. We're now about 3 inches from the bottom of the hole, and we're still holding it at 55%. And you notice that the pitch is nice and consistent, and if you're looking, the coolant is spraying out all over the place. It finishes up its cut. Note that it's going back to that 50 RPM as it comes out of the hole. Then we'll gather up a couple of the chips and take a look at them and show you how that went with the deep hole drilling guidelines. There we go. So we're just going to gather up. Now, inside the machine, the chips are kind of sprayed all over the inside of the machine. Well, that's what you want to have because we have ample coolant flow and pressure to keep those chips moving, and it should be spraying all over the place in there. Okay, so here's the chip that we produced, which is actually the same chip that we made with that shorter drill, so you can kind of see what we got going on there, and everything went just fine. So once again, anytime we have a tool that's 9 times D or deeper, we want to make sure that you follow the Allied deep hole drilling guidelines. Once again, it's a safety issue. We want to make sure you do that. Bill, if you want to come back on in here, you can have any closing comments that you have.
Yeah, thank you. Smooth as butter as always, Rob. Great job.
Thanks.
So just a couple of takeaways with this. First of all, thank you for taking the time to watch this live video, the demonstrations, and kind of going through the beginning. But the big thing with high penetration drills today, as we know, everybody needs their parts yesterday. Excuse me. So everybody needs them yesterday. So switching over to a high penetration drill is going to increase your throughput, get your parts off the machines faster, and like I put in that one case study, solid carbide, we're right up there with penetration rates, sometimes exceeding the penetration rates of the solid carbide, limiting the amount of tooling that you have sitting inside of your shelves. One holder, many different inserts, again, decreasing the time of having to be able to send out the solid carbide drills and getting them reground. So again, just my big takeaway is being able to provide you with the high penetration drill that you need to get the parts to your customer, and we appreciate you taking the time to spend it with us this morning. So thank you. Until next time, see you then.